Okay. Um, Hello. Yeah, so I'm basically just uploading this video because I thought that this problem was really cool. Not much to say, really, other than that. Um, yeah. So first I think I'll explain the problem, then I'll sort of explain a bit more about why I uploaded this video in the first place. But yeah, for now let's just get straight into the problem. So, the problem source, if anyone wants to try this out for themselves, is the 2013 AIME II problem 11. Um, So anyway, with that, let's have a look at the problem. So it says let A be the set from 1, 2, 3, 4, 5, 6, 7, and then let n be the number of functions from set A to A. So what that means is, let's say that I have like 1, 2, 3, 4, 5, 6, 7. Then I have the output set, which is change the thickness a little bit here. Let's say that's also 1, 2, 3, 4, 5, 6, 7. Then our function somehow goes ahead and maps these two to each other. So maybe 1 goes to 1, maybe 2 goes to 1, maybe 3 goes to 2, 4 goes to 3, 5 goes to 6, 6 goes to 5, and 7 goes to 7. Maybe that's our function. But basically, what a function from set A to A is doing is it's giving you a rule for how these connections are made. Okay, so now let's look at what the actual problem is telling us that f does. So it says that f of x is a constant function. So to understand what that means is you're saying, okay, if I plug in any number into f of x, so let's actually just for clarity, let's call f of x like let's call it c of x because it's constant. Let's call it c of x. Then no matter what I plug in for x, if I plug in 1 or 2 or 3 or 4 or 5 or 6 or 7, it'll always give me the same number. So if I plug in c of 1, okay, that'll give me 5, let's say. C of 2, that's also 5. C of 3, that's 5. C of 4 is 5. C of 5 is 5. C of 6 is 5. C of 7 is 5. So that's basically what it means to say that f of x is a constant function. Okay, so we should account how many ways is that possible. Perhaps that's a bit easier said than done, but we'll have a look. So the first thing to kind of think about, or at least that I was thinking about when I was looking at this, is okay. What we really care about is let's say I take any number right in this set. Let's say I take 3 and I plug that into my input right into this inside f of x. And I say, okay, well, f of 3, we don't really know how that's mapped yet, but let's say just for fun that's equal to 5, right? Then what I know, and let's say that my constant value is always 1. Let's say that f of c of x always equals 1. Okay, then what I know is, okay, let's say f of 3 is equal to 5. Sure, it doesn't really matter, but then what I know for sure then is that f of 5 must be equal to 1. Okay, so that was sort of my initial thoughts. Okay, so knowing this to be true, the sort of solution kind of starts building itself from here. So we say, okay, well, how many of our inputs are mapped to the constant, right? So let's have a look at this mapping here. Obviously, this mapping is not a valid mapping for f, but yeah. So we notice that like 2 of these are bound to 1. Right? I say that maybe 1 is what our constant function is going to return. It's always going to return 1. 2 of these are returning 1 right now, right? So basically what you have then is you have some part of the set which will map you straight to what your constant is going to return, and then some part of the set that's going to map to the things that map to the constant. So, for example, in this little example that we computed here, f of 5 is one of the ones that maps to the constant, which we said was 1. and 3 is one of the ones that maps to something that maps to a constant, because it maps to 5. So basically, this is how our set sort of needs to be set up. So now we can actually just start counting it directly. So let's go ahead and give us. Oh my god, I don't know how to navigate on this at all. Okay, there we go. Okay, so let's get a little bit more space here. So first things first. We need to figure out, okay, how many ways are there to pick what our constant value is? Okay, well, it's pretty obvious, right? We have 1 through 7. Actually, maybe I shouldn't say it's pretty obvious, but well, our set includes the numbers 1 through 7, and we need to pick one of them to be our constant. So we got 7 ways to pick the constant. Let's write that up here. C. There's 7 ways to pick that. Okay, so then we need to figure out, okay, how are we going to map it? Okay, so at this point, we can just kind of casework it, right? Let's say that we only have, oh, okay, so let's say that all of them map to the constant, right? So notice also, this is sort of a key thing. F of C must equal C. And so to demonstrate why this is true, this will actually come up. This is actually pretty important for how we're going to count the rest of it. But the reason why this must be true is because let's say that we're looking for this, right? Like f of 5 is equal to 1. Okay. Let's say that I plug in 5 as my input, right? So then I get, okay, f of 5. Then this becomes f of 1, right? And then that needs to equal 1. And the reason why it needs to equal 1, and you can't have like f of 1 being equal to 3, and you say, oh, well, okay, 3 maps to 1. And you say it's like that. It doesn't work, because all the ones that'll map you to the constant, you could also plug those in as inputs, right? So, 5 is one of the things that maps to our constant, but if I plug in 5 as my inside input, then that outside input still needs to map to our constant. So we know then that f of the constant must be equal to the constant, because then our mapping inputs, like 5 here, will also go back to the constant. So that's why f of c is equal to c. Okay, that's our next equivalence. Okay, so now we're dealing with the 6 other remaining numbers, because we already know what the mapping for f of c is. So then, in the 6 other numbers, let's say all of them also map to c. Okay, how many ways are there for that to happen? Well, there's exactly one way, right? Okay, there's this one way for all of them. So how we can write that in a more generalizable format is by saying, okay, out of the 6 numbers, how many did we choose to be mapped inputs? Okay, well, we chose all 6. So our first thing is going to be 6 choose 6. There's 6 choose 6 ways to pick 6 of the numbers to map to the constant. Okay, so that's our first thing. Okay, now let's say that we picked 5. 5 of our inputs to map to the constant. Okay. Well, of course, there's going to be 6 choose 5 ways to do that, right? And now, for our one thing left over, it can map that the input that's left over. Well, it can map to any of these 5 that we picked. So there's going to be 5 ways to do that. Okay. And now, for our next one, I think you kind of see where this is going. Okay, so we need to pick 4 things that map to the our constant. Okay, now for the other 2, so the remaining inputs, they could map to any of the 4. Both of them could map to any of the 4. So for the first one, there's 4 options. For the second one, there's 4 options. So that's 4 times 4, that's 4 squared. 4 squared. Okay. Now I think that the pattern will really start to emerge for you. So now we're going to go 6 choose 3 now. I think intuition remains the exact same. We're picking 3 of these to be mapped. then for the other three, they each have three options, right? So they could be mapped to any of those three that are mapped to the constant. So that's going to be 3 to the 3. Now I think that the patterns become pretty apparent, so we can go and write the rest of it out. 6 choose 2 times 2 to the 4 plus 6 choose 1. Now the reason why there's no exponential after 6 choose 1 is because it's 1 to the 5, right? Doesn't really mean much. They all only have one option they could go to. So you don't need to write the exponential, right? 1 to the 5 is just 1. Okay, now you might be wondering, hey, well, are we going to do 6 choose 0? The answer is no, because, well, if 0 of them map to the constant, then you don't have a valid case. So this is our final answer. Now, in test, you would need to find. Of course, this is from a math competition. Right? This is from the AIME. So if I was sitting for the 2013 AIME, then yeah, I'd have to find a way to evaluate this. And I think that I think that there is a combinatorial identity that'll evaluate this. That'll evaluate this for you. I'm not really familiar with any combinatorics identities because I just started learning the subject a couple weeks ago. But yeah, I mean, this looks kind of like binomial theorem. Maybe it's not binomial theorem. Actually, it's definitely not binomial theorem. But I mean, I think that there is an identity that'll do this for you. But I don't know it. So, and since we're not taking the test, and we don't need to solve it as if we're taking the test, we can go ahead and use Wolfram Alpha to evaluate this for us. So let's go ahead and plug that in. So we have 7 times 6 choose 6 plus 5 times 6 choose 5 plus 4 squared times 6 choose 4 plus 3 cubed times 6 choose 3 plus 2 to the 4 times 6 choose 2 plus just 6 choose 1. And so now we get our answer, 7,399 ways to do this. However, any of you who are watching this, who have taken the AIME, will know our numbers always have to be between 0 and 999 for an answer. So now you might be wondering, hey, did we do something wrong? And let's go back to the problem. We'll have a look. And no, because we see, and this is the clue, find the remainder when n is divided by 1,000. So this is how you know that our answer is going to be over 1,000. This is how they always normalize it. So our answer is 7,399. Well, that mod 1,000 is just 399. I think I pulled it up right here. Let's have a look at the solution. It should be 390. There it is. They used a pretty similar solution to what I did. It looks like. Yeah, they labeled it in tiers. I don't really know what. I guess they're pretty much talking about the same thing. I don't really know what this kind of tiered system is. But yeah, I mean they're basically talking about the same things. This is our mapped inputs, and then this is the things that are mapped to our mapped inputs. Things that map to the constants. So yeah, this is equal to 7,300. Now the one thing I am kind of curious about, because I only looked at the answer before I decided to upload this video. Did they actually explain how to evaluate this sum? No, they just said that's equal to 7,399. Let's have a look. I don't know. I guess they expected maybe there is. Wait, where did the what? Where did the maybe that simplifies. I don't know. I guess that there is no really fast way of doing it. Okay, well, maybe there is a fast way of evaluating the sum that I just don't know about. I figured that there'd be some identity for that. Yes, if anyone's watching this that's better than me at combo, or really any good at combo, do let me know about how that was done. Yeah, so that's pretty much how I solved this problem. Now, if you're wondering sort of how I found these problems, I've been doing the problems from this site here. So my pretty much my requirements, it has to be an AIME problem. I don't know what the fuck the rest of these contests are, and there's no way I'm spending my time doing AIMC 12 problems. That's like way too easy. Um, so yeah, it has to be an AIME problem. It has to be problem 8 or higher. So you'll notice like this is pretty good. But then they'll put some AIME 5s in there, and it's like, okay, I'm not doing that shit, right? Yeah, like this problem 6, like problem 2, like yeah, that's yeah, come on. Yeah, so I've just been going through all the AIME problems that are from at least 8 plus, preferably 10 plus, but you know, there's a couple hard ones. I've done a lot of these. Um, I'm mostly just working on kind of the easier to understand combo problems. Uh, I think I'm not really good at like expected value problems or path counting problems, stuff like that, or region counting. That's another one where I sort of want to get better. Um, so right now I'm just working on really easy to understand combo problems like this one. Of course, AIME 12, AIME 11, usually fairly difficult. Um, but yeah, I will say these are also earlier AIME problems, so they're not as hard as the newer ones. Yeah, so I've solved a fair bit of these. I think that the two problems that I attempted to solve that I got wrong were this one, 2009 AIME problem 10, and then there's a problem 14 somewhere. This one, I think, is the one. This is not the one. Hang on. There is one problem 14. Maybe it's this one. Yeah, this is the one. This handshaking problem. Uh, it, if anyone could sort of, I haven't attempted to read the solution yet. If anyone could give me a hint on this problem, I would really appreciate it. The way I approached it was sort of looking at sort of, so I sort of modeled it as like a graph. You know, you have points for each person, and then each edge on the graph is sort of a handshake. Um, yeah, I didn't really understand how to do this. I was thinking maybe you could do recursion once you have 3 points and sort of recurse up from there. But it didn't work. I didn't understand how to do the recursion. I tried case working on like different loop cases in a graph too. Um, but yeah, I couldn't actually end up computing an answer for this problem. So this one I got wrong. Other one that I attempted that I got wrong was this one, I think, 2009. Yeah, this was the one. I really thought that I got this one right. I was almost sure about it. Yeah, but I made a computation error. Barely got it wrong. Kind of rough. But yeah, other than that, I've solved most of these AIME problems that are AIME 8 plus. I'd say not all of them, of course. I haven't attempted all of them because I just don't have that much time. But yeah, yeah. The reason why I uploaded this was mostly just because I thought that this problem was pretty cool. Uh, and recency bias. Well, I just solved it today morning right before I recorded this. Right as I woke up, solved this problem. So yeah, that was sort of that. Uh, yeah. I don't know if I doubt that anyone will watch this. This is sort of just for my own chronicle. Yeah. Thanks for watching.